Hello again, everybody. I'm Gavin, and I have a day job. I'm a consultant, and I guess what I do is try to apply some of the things that we've learned over the years about delivering software to this area of data and databases and data engineering and so on. And for the next half hour or so, I'm going to talk about, well, how we got to where we are with database development, as well as some of the approaches we can take to addressing its challenges. So I've attempted to frame this in a way that isn't so much about platforms and tools, since at a meetup like this, no two people are using the same platforms and tools, but more about how we think about the work we do and the ways that we do it. So I think tools are mostly off topic during the talk itself, but potentially on topic for those open spaces afterwards. And on that note, I find it really difficult to stage manage questions during these Zoom presentations. I can never figure out how to see them as we go along. But I guess feel free to talk amongst yourselves in the chat and maybe think of some topics for those open spaces. And as a final note on that, if you haven't been to this meetup before, I definitely recommend hanging around for the open space. They're one of my favorite parts of these events, and the facilitators are super slick at getting it all right. And even if you're not familiar with the open space thing at all, that all sounds a bit weird, rest assured that it turns out to be pretty non-weird and often really useful. So I think the reason this topic is interesting, at least to me, is that applying what we know about continuous delivery to data and databases has historically proved to be somewhat problematic, certainly compared to the way we deliver application software. For instance, we don't really do this kind of thing anymore. And why not? Well, imagine we wanted to write some tests for the methods in this class. We'd have to think of a way of faking out that global sales variable, and well, that tends to get complicated quite quickly. And then assuming there's a bunch of other methods that could potentially modify this variable. Well, when we look at the code for those methods, well, that global state can make it difficult to understand how they work, or even if they do work. And as for scaling, well, if we attempt to scale out this application, then, well, every instance, I guess, would end up with a private copy of this value. And presumably we'd have to reconcile those somehow. And again, that gets complicated pretty quickly. So as application developers, we've generally stopped doing things like this. And another thing we've had a lot of talk about over recent years is this related notion of monolithic applications. So what do we mean by this word monolith? Well, I actually don't really want to get too bogged down with this. So I think to coin a phrase, we know one when we see one, right? And it's a key characteristic of these systems that they're hard to deploy. As well, generally the whole thing has to be redeployed every time we need to change any aspect of it. And often these systems are difficult to change, as we're never quite sure what might break. And if we do make a change, well, we have to do that whole late night thing in order to redeploy everything. So we shy away from making those changes. We shy away from doing features. It becomes a vicious cycle. And these systems are frequently difficult to scale, as, again, it's often difficult to scale the individual pieces independently. So we end up trying to scale the whole thing, which takes us back to that complicated deployment story, which we don't want to do. And if we try to scale out, we run into this problem of the global state not being global state and so on. So over the years, there have been a few attempts to address all of these issues, starting with, well, what we used to know as service-oriented architecture. And then some consultants came along and all of our services had to get on the bus. And then some other consultants came along and all of our services got off the bus and turned into microservices. And these could be deployed independently and scaled independently, in part because, well, we didn't contain much in the way of state, which meant they could be deployed to infrastructure that was immutable. Now, I happen to think that immutable infrastructure is a really important enabler of good stuff. And what it means to me is this, that we define our deployment packages in such a way that they contain everything our application needs to run. The operating system, supporting services, the web servers, and so on, and in addition to our application code. And then we never touch it again. We leave it alone. And when it's time to deploy a new version of the application, we just create a new version of our package with our application, all the dependencies, all the services. And this probably looks like, a container or a VM image. Then we destroy the old infrastructure and provision a new, complete with our running service. And this approach has many benefits in terms of reliability, maintainability, other ilities, and overall like surprise reduction, which is really the whole point of this. But well, it turns out that there's a key technology that's been enabling many of these innovations in software development, namely the database. And for now, we're talking about traditional relational databases, such as the one in this box here, which could be Oracle or Microsoft SQL Server or MySQL and so on. So what goes on inside the database? Well, it turns out that the database is a giant bundle of shared state that all of our services can read from and write to. And all the components are tightly coupled together. I think if you look around the back of this box, you can see all the coupling. And the infrastructure, of course, is really expensive and requires patching all the time, database patching. So really, in effect, it seems like we've managed to outsource all of the hard stuff about software development to this magic box on the right here. And, well, in most cases, obviously, outsourcing is a really good idea that never fails to deliver on its objectives. But in this case, we're left with database systems that are hard to test and hard to deploy, hard to change, and hard to scale. So what is it that's so special about databases that we're prepared to put up with all of this hard stuff? Well, obviously, it's precisely this giant bundle of shared state, also known as the data in the databases, that really matters. And in most contexts, when we think of our application's data, the word security shouldn't be too far behind. And when we talk about data security, often we mean some combination of these three things: confidentiality, integrity, and availability, which are generally things we need to worry about with respect to our data, but maybe less so with respect to our application code, our binaries. Now, many of you may have seen this graphic before. It's known as the CIA triangle by, I think, people who wish they were on a secret jungle mission instead of a change review board meeting. And so by confidentiality, we mean that we really don't want our data to be seen by the people who aren't supposed to see it. I mean, if we accidentally leak our application source code to the internet, well, in most cases, the only consequence is a few more smart remarks from our buddies at the Haskell Meetup. But if we leak our data, particularly if that data relates to people, the consequences can be severe indeed. We also want our data to have integrity. We want to be sure that when we read it, it's the same as it was as when we wrote it, more or less. And now for our software, for our applications, this isn't too hard. If we think there's something awry with our deployed application, well, we throw it away, we deploy it again. And we need our data to be available whenever we need it. I mean, if GitHub is down, well, we just go to the pub, or at least we would if there wasn't a pandemic on. But if we can't get to our data, if our data is unavailable, generally we can forget about the pub for a while. So what does this mean for our databases? Well, it means they're these magic boxes with really onerous security requirements, and deploying them is really difficult, and the infrastructure is really complicated, and patching. So what do we do about this? Well, in many cases, the answer has been to hire dedicated professionals to look after our databases, known as DBAs, or database administrators, or database engineers, or more generally, data professionals. So where do these denizens of the data center fit into the continuous delivery picture? Well, I think in many ways, the database teams were the original DevOps teams, in that they acted as a contraceptive for the developers and the ops teams to make sure nothing ever got delivered. And one of the ways they did this was by having rules, such as, well, all database changes must be approved by the database team. And I think we've all heard that. And how does that usually play out in practice? Well, the developers, they write their code and they're ready to deploy their change. Then the database team says, no, you can't do that. Your function to calculate the total of all the sales is scanning the whole sales table. And then what happens? Well, then the developers go and complain to the product team who say, yeah, don't worry about those guys in the basement, just get our feature shipped. So really that whole fuss is a waste of time. And the answer to that, if you have that problem, is that if this DBA code review has to happen, it has to happen before the change is merged. And it's all too common, I think, to find that that pull request or whatever process that causes that change to be merged, that happens in a place where maybe the data team can't see it or don't want to see it or aren't being encouraged to see it. Now, another variant of this is that all such changes must be physically carried out by the data team. And this is often justified on the grounds of like SOX compliance or PCI compliance or compliance. And this is why, we can't automate that. And this is why we're in this world of manual procedures and deployment checklists and so on. And it's funny, in a previous life, I had cause to read big chunks of the Sarbanes-Oxley or SOX Act, and I never did find that bit about storing spreadsheets in Confluence. So how do we move forward from here? Well, I think for me, and in many other cases, the answer has been to try to apply what we know about delivering software to this work of delivering databases, which are, after all, software. I think it shouldn't be controversial to say that success with software delivery starts with version control. And, aside, there's a company called Redgate, I'm going to mention them later, who make a couple of different tools in this space. And their people present at a lot of conferences, a lot of database conferences and others, about improving delivery practices, which is great. And for years, their people say things like, oh, well, I was at this customer with no source control and no tests and no deployment pipeline for their data assets. And I'm sitting in the audience thinking, yeah, these people are having a laugh. I mean, where are they finding all of these customers with no source control and no tests for their data assets? Well, as it turns out, I was the one who'd been leading quite a sheltered life. And not only have these customers existed for years, but they still exist now and quite possibly are still being created. What about deployment automation? So I'm going to skip over this for now, but it seems that from a database perspective, how we do deployment is basically determined by how we represent our database in source control. And as for testing, I think this is something that's traditionally been problematic in the data sphere, and I'm going to touch on a couple of approaches for that. So how do we go about adding our database objects to source control? Now, this is something I've thought about loads over the years, and I still don't think I expressed this quite right. But one of the things that occurs to me is that there's quite a lot of stuff going on with SQL code. So these are recognizably source files, right? And one of them creates a table and the other one creates a stored procedure. I think both of these will work on most platforms, but we don't really build them into anything. They kind of just are. So they're a bit like artifacts, since this is what gets deployed, or maybe they're a bit like deployment or configuration scripts, since this is how we do the deployment. And this first one here defines a structure of the data, and the second one here defines some behavior, some procedural behavior. But it's not quite that simple, because the table script has some behavior too, such as this list of permitted kebab types. And interestingly, that behavior is specified in a declarative manner rather than a procedural or imperative manner like the stored procedure below. And this declarative manner is really the original paradigm for SQL. And what happens when we want to make a change to a table? So in version 2, we're introducing support for a new source. And unlike the chili sauce, this one defaults to off. But how we make this change, of course, depends on where we start from. If the table doesn't exist, we have to create it from scratch. If the table does exist, we have to alter it. So this language, this DSL, is not by itself idempotent, unlike more modern tools such as Ansible, which are definitely idempotent all the time. Oh, and how do you add support for a new type of kebab? I think maybe save that one for the next whiteboard coding interview you have to do. But in fact, if you dig through some of the old literature, like one of the things that's touched on and we can reflect on is that there's more than one thing going on here, as they used to say, more than one sub-language. One that maybe creates these data structures, one that returns data back to us, one for doing updates, and maybe some procedural stuff for creating our procedure that did the reporting. But all of these different things, these different sub-languages, are expressed through that same high-level DSL, even though they turn out to have very different semantics. So can we think of any other tools that have slightly confusing semantics? Well, what about the ultimate DevOps tool? Now, I think anyone who fully understands the semantics of Excel may be at the wrong meetup, but Excel isn't just the ultimate DevOps tool. It's the ultimate end-user reporting tool. But in this space, it has some competition. So what do these tools all have in common? Well, they're all like interactive data analysis type tools with these embedded formula languages. And as anyone who's ever tried it will know, these embedded formula languages are super difficult to version and to test and to package. But that's okay then, as these are end user tools, right? And the whole point is that they're so simple to use that they've enabled this self-service analytics revolution. Except, of course, if we look at JobServe, we see there are hundreds of openings for Power BI developers, Tableau developers, MicroStrategy developers, Excel developers. And because these developers are developers, they occasionally attempt to do developer-like things, such as, well, source control or testing or continuous delivery. And I think the good news I have regarding doing of fancy DevOps tricks involving these tools is, I think it's only a month until the pub opens now. But seriously, and this might be the first key takeaway of the talk, I think by the time you're thinking about writing unit tests for your pie charts, you should probably be thinking about writing a computer program in a general purpose language to display those charts on the screen. So what does this have to do with our SQL scripts? Well, students of history may also be aware that SQL itself was originally intended as an interactive tool for users to construct and query their data, I think mostly used in the defense industry back in the day. So this may not have an animated bubble chart, but it was a lot better than what was available at the time. I mean, clearly I'm relatively youthful, but even I can remember working in a bank and we had to ask another team to give us a list of all the customers who are more than X weeks behind on their mortgages, I think it was. And the response was that this would take 12 weeks. And it would take 12 weeks by a team of like 10 people with a computer that cost like millions of pounds. So this at the time was really, transformational. And I think that this is the root of this impedance mismatch between like SQL and things like source control and unit testing and so on, is that this is an end user tool that hung around long enough to become a developer tool. Now, I don't think that this mismatch is as difficult to solve for SQL as it might be for some of those graphical tools. I mean, after all, these scripts are text, right, which we could feasibly store in a version control system. And the main challenge is to make the deployment operation idempotent, which is to say that regardless of the initial state of the system, we want to end up with the table looking like the top box here. And this must hold true no matter how many times we apply our change. So what this means in practice is that if the table doesn't exist, we need to do the stuff at the top. If it does exist, we need to do the stuff at the bottom. If it exists and that column is already present, then we need to do nothing. Now, it is, of course, possible to write out all that logic in SQL or in some other language. And I've definitely worked at companies that do that. On the other hand, there are a large number of tools in the market to help us address this challenge. And now, some of these tools take a desired state type of approach where you specify what you want the end state of the database schema to be, and this tool will figure out the steps for how to get there. And some work by storing and replaying a list of migrations, which are the steps required to get to your desired end state. And you know what? All of these tools work, but some of them have some rough edges. And I'm not one to complain about this, since it's these rough edges that have, by and large, paid for the house that you can see in the background here. And if this stuff all works seamlessly, I might have had to get a proper job, like being a certified safe agilist. And what these tools have in common is that they enable you to manage and deploy your database objects from source control as well as from your CI server. The other thing they have in common is that all the tools on this slide allow you to specify your database using the native SQL dialect of the platform without any additional plumbing code. In other words, they're tools for these people. And I've noticed something about how we write software these days, which is that there seems to have been this convergence in the way we write and package our code. I mean, a few years ago, we figured out we could do JavaScript on a server. And from there, I don't think it's a great leap to doing server-side rendering of our framework sites like it's 1999 again. And in the other direction, or more recently, we invented Webassembly. So we can do stuff that you'd normally do on a server or on the desktop, in a phone app, in the user's browser. In fact, it's almost as if we're managing to organize our application features and code kind of by context rather than by the implementation detail. But this doesn't seem to have happened with these database-only development teams. And on a related note, I had a conversation with someone a few years ago with a client, and he was saying that microservices are rubbish because, well, now we had to keep track of changes in 100 different databases rather than just the one. And actually, the reason we were having this conversation was that having 100 different database schemas in a single workspace using one of those tools had exposed one of those rough edges. So leaving aside the question of whether it's easier for a human to keep track of, one database that does 100 things or 100 databases, each of which do one thing. And also leaving aside the question of what keep track of means. I mean, I didn't probe this at the time. I think it was to do with Confluence. But is it reasonable to have one person or one team keeping track of changes in 100 different projects? When much more recently, at the end of last year, I was working with a SQL Server Microsoft customer using Microsoft's tool for this, Azure Data Studio, which I downloaded and installed. And I created my first project, where project is more or less the source code for a single database. And the next thing that happened was I got this pop-up. Now, I think this is gone from the current version of the software. I was using a pre-release then, or at least I can't find it anymore. But I saved a picture of it then for just a moment like this, as I think it reveals a super interesting assumption, which is the person who uses this computer maintains a bunch of database projects. And these projects are stored in a common location, maybe not shared with the applications or services that depend on these databases, and presumably not co-versioned unless everyone who uses this feature is also using sparse checkout. And the application code, well, presumably that's somewhere else, maybe even on someone else's computer. And well, as I said, this seems to have disappeared, and that's interesting too. Possibly no one ever clicked yes. And now, in keeping with the Meetup tradition of shoehorning in a reference to Conway's law, I think this is the moment here. What do we think are the likely consequences of having our database structures maintained by a different team than our applications and services that depend on? I think I'll leave the answers to that question for the open space at the end. But in the meantime, what else can we do? Well, there's another category of tools that allows us to embed our migrations, i.e. the steps we need to do to get to our desired state, into our application source code. And most widely used programming languages have one or many libraries for doing this kind of thing. And I'm sure most of you are familiar with at least one of them. Now, these tools vary quite a lot in how far abstracted they are from the native SQL stuff on the platform. But the advantage of this approach is that given that we embed our migrations in our application or service source code, this means that it's very easy to co-version unless you're doing super fancy tricks. So we've kind of eliminated this problem of the untracked dependency on the database developers. Now, there might be some circumstances in which we want to use one of those database-specific tools here. But the important thing is that the database development is managed alongside the application development by the people that develop the applications. So what's the downside of this approach? Well, it makes this kind of thing a bit untenable, doesn't it? What about testing? So with code that directly interacts with the database, this is something else I've talked about endlessly. There isn't really any such thing as a unit test, I don't think. And, in general purpose languages, it's pretty common to mock our database connections so that we can test our application logic. But if we're hitting the database directly, well, we always have this real external dependency. So our unit tests are never going to be pure unit tests. And now there are a couple of approaches to this. The easiest one is to say, well, look at that external dependency that can't be mocked. We can't write proper unit tests at all. So pub. And the other is to accept that our tests are going to be a bit impure and make the best of it. So depending on the platform, there are some ways to write tests inside the database for procedural code inside the database, like stored procedures and functions. And there are ways of mocking. And these things are super platform specific. So I think that's best left for individual research. On the other hand, end-to-end or integration testing, this can be pretty important for operations that affect data or affect a lot of data. And I'll return to this shortly. But for now, I'll say that end-to-end testing of database applications, well, it has all the problems of end-to-end testing of every application, meaning the tests are slow. The feedback cycles are long. The setup is painful. Worse still, if we have to do teardown, that's more painful still. And in the context of CI, I think my go-to at the moment to this is to pre-stage as much of this setup as we can in containers, some description. So where does this leave the data professional? And if you want to know why the NoSQL databases and the managed platform databases in general have become so popular, I think this is the reason why here. So on this topic, this is an interesting question. I think one of the big differentiators of the NoSQL databases, which I realize I'm conflating with the cloud databases where we mostly encounter them, is that the compute is kind of separated from the details of storage. And in the past, the reason we created those monster database systems was that for whatever reason, we needed our compute to be close to our data. Whereas you can see from this example, which is from an old talk, that in this world, I don't really need to worry about all that persistent stuff. It all kind of happens in the background. Now, because this stuff is taking place in our web service or in an API, this can be deployed to infrastructure that's immutable with all the associated advantages. And that said, I think for many developers, particularly in that enterprise environment, is that I can do my provisioning like this without consulting the angry mob in the basement. And obviously, yes, this operation is idempotent. Even better, when it comes time to use this data store, well, the context can be injected, which makes this service even easier to test. And, a few years ago, I used to work at one of those big outsourcing companies, and I was having a chat with the boss as, that's how you climb the greasy pole. And it went something like this. I said, you see all these people who come to work every day and write stored procedures for Oracle and SQL Server. I said, a few years from now, from then, this isn't going to be a job that people do. And all of these people here are going to have to develop new skills, either as generalist back-end developers, or in this business intelligence space, as we used to call it before data science was invented. And if they can't do that, they may have to become certified safe agilists instead. And the boss said to me, well, yes, you might be right. But for now, we are charging the government a bale of cash for these people to sit here and write stored procedures for Oracle and SQL Server. And then I was enlightened. But still, I think I was right about those jobs going away, but maybe I underestimated the length of time this would take. So what does the future hold for the database profession? So on the face of it, becoming a big data engineer has many advantages. I mean, there's no need to argue about index fragmentation with those web developers because there aren't really any developers unless you count the Tableau developers, and they're too busy fixing all of their wrong formulas because they don't have any tests. So what's big data all about? Well, for those unfamiliar with the space, hopefully it's all on this slide here. And we have some data sources on the left, which might be relational databases or log files or document stores, application generated or externally generated, or of course Excel, and some process that loads all of this data into our lake. Now, from the lake, we transform this data into some form that's more palatable for our consumers, generally a dimensional model of some kind. And this might be stored in a number of different ways, in a database, a relational database, or maybe some other structure. And actually, jumping back to that previous slide about tools, I think this here might be the kind of new sweet spot for those database-specific tools. I mean, if this model here looks something like a relational database, meaning it's Redshift or the Azure Data Warehouse or the Google one, and we've designed things in such a way that we aren't really tightly coupled to the interfaces on either side, then yes, these databases can be developed and managed as if they were independent services, and that means they can use their own tools. Anyway, after that, the end users or the data analysts, well, they consume our data through a number of tools, including, of course, Excel, which is where all data is born and all data goes to die, as well as a number of more specialized tools like Tableau and Excel and the various types of notebook. And I think the job of data engineering mostly consists of filling in these arrows. And the good news is that these arrows mostly look like code that reads some data, does some transformation, and outputs some new data. And because it's code, we can use all of the tools we normally use for code, for linting and testing and building and packaging and deploying. And this makes a lot of the hardness of the problems I was alluding to with relational databases go away. More importantly, this is kind of neutral of the storage structures. And we can redeploy this as many times as we like to our immutable infrastructure. Now, there's one thing worth calling out here, which is this. The Spark session is it's an embedded dependency, and we depend on it to do the big data magic behind the scenes. So do we need to mock this out to write proper unit tests? And I think the answer to this question is kind of the same as it was for the relational databases, which is that this isn't the time to get hung up about the purity of our tests. When we write ETL or ELT code, whether this is with SQL or Scala or even Excel, we're always dependent on this external processing engine of some sort to do the magic. So much like in the relational database cases, it's possible to mock this out, but maybe not worth it. I mean, we're not supposed to mock what we don't own. And again, in these kinds of systems, it's generally easy to fake the environment, either with real infrastructure that's ephemeral that we can stand up and stand down for every test run, or even with a container, which is kind of naturally immutable, that reflects the desired start state of our testing. Excuse me. Now, this is not to say, of course, that it isn't beneficial to have maybe some of the computational bits of our pipeline abstracted into functions that can be tested in isolation. But yes, just like in the relational world, there are some performance dragons there, which is why it's important that we do testing. Now, this is an interesting one, and it's one I've come across before. And the uncharitable explanation for this is that these data scientist characters are too lazy to write tests, but I think it's a bit more nuanced than that. I think these exploratory type of activities are maybe closer in function to like the end user reporting, like with Tableau or Power BI, or as I was saying back in the day with SQL, in that these things are interactive and maybe don't have those strongly defined outcomes, which is why we call them exploratory. However, just like when we have to take an Excel macro from a trader and incorporate it into our ETL process, when we have to take a notebook from a data scientist and incorporate it into our pipeline, well, this is the time when we need to think about adding tests to make sure it works in the way we expect it to work, which is really what we mean by testing. And whilst, many of these techniques might indeed be non-deterministic given non-deterministic inputs, especially large and non-deterministic inputs, I found this is very rarely the case given controlled inputs. And this is another common complaint about writing tests in the world of ETL and ELT, and it's not new. I mean, you'll remember in the bad old days, we used to restore copies of our production database to the dev environment so that we could do testing. And remember that we've all stopped doing that because if we did it now, we all go to jail or we get fined millions. Good. And the same thing applies to our data lake. And the source of all this confusion, of course, is that we're confusing or conflating two different types of testing. Do we want to test our data loading processes with real workloads? Well, yes, of course we do. And where's the best place to do this? It's where the real data lives, or as close to it as we can manage. What about functional testing? Well, we can do this with much smaller amounts of data. And this is the thing. For all of our big talk about advanced algorithms, a lot of what goes on in these data loading processes is arithmetic. And arithmetic works, well, in broadly the same way with 3 integers as it does with 3 million. And I think often the challenge here is having recognized that however big our data loading process is, we can test it with 10 or 20 or something rows. The hardness comes in identifying which 10 and 20, and that's the work. And do we need mocks? Well, again, maybe not. It might be as easy to fake out the infrastructure with containers or ephemeral infrastructure as it is to mock the Spark or whatever runtime from inside the code. So I'm a bit over time. Unfortunately, that's the last slide. So to recap, big data isn't that different from small data, except it's often easier to abstract our logic from our storage in the modern data stores. And for those databases that support applications and services, these need to be maintained alongside the services that depend on them. Some platforms make this easier than others. Deployment, idempotent all the time. Whether we do this through scripts or we do this through tools for the database or through separating our logic into services that can be deployed to ordinary infrastructure. And yes, testing is difficult and mocking is difficult, and mocking the DBAs is easy, but they're our friends really. But immutable infrastructure, containerized or otherwise, can be our best friend. So that's about all. Thanks for hanging on this last half hour, and I look forward to talking in the open spaces.